If you're given a scenario of an inclined plane where there is a spring, which is at the natural length at this position, and this is a block at x equal to 0, released over here, it hits the spring at 8d. There's another position given at 6d here, and after that it compresses a little bit, moves at 10d, measured from the top in a slant way, and it is at rest at 12d once again. So in this entire system, they have drawn curves for us at x equal to 10d. These are the energy bar charts. This is kinetic, this is potential of the entire system, and this is potential of the spring. So they're asking how will these energy bars look like. So we know that this is already given that this entire system is frictionless. It's given somewhere over here. So I know that the entire energy is conserved. Let's count the number of blocks over here. This is 7, this is 2, and this is 3. So that's 12 E naught. So 12 E naught has to conserve, right? At x equal to 0, the block is released, so there is no kinetic. The spring is sitting peacefully without any stretch or compression, so it is also at 0. So entire 12 will come at the potential. Next at 6D, once again, the spring is not compressed, so definitely the spring is at 0. Now for the potential, we have to do a little bit of math here. We are given the potential at 10D as 2E naught, right? So, and remember that the reference is to be taken as 12D. So with respect to 12D, which is marked over here, I'm just going to draw a horizontal line. Now, from 12D to 10D, what is the difference in the slant position? Obviously, that's 2 units because at 10D we are given a position. So this difference of 2D corresponds to an increase of 2E naught, of course. So we are going to 6D. So it makes sense that for every D, we have an E naught increase in the potential energy. So for 6D, which is basically an increase also of 6 because from 12D to 6D I have 6 units. So for 6 units I have 6 E naught as the potential. So the potential goes to 6 E naught, and the remaining out of 12 E naught again 6 is the kinetic. Right, this is how it should look like. Let's move on to the next one. We're using the scenario that it is released at x equal to 0 and it is again at rest at 12D where the spring is compressed maximum. We need to derive the equation for the spring constant K in all these terms. So we're going to conserve the mechanical energy, of course. At this point, the only mechanical energy that we have is the gravitational potential energy, which is 12 E naught. Can we agree on that? Because we just agreed that for every D, there's an E naught increase of the potential. So x equal to 0 and x equal to 12D, there's definitely a 12D difference. There has to be 12 E naught. And at this point, once again, the potential is 0 because it's already given in the question that at 12D potential is 0. Kinetic is 0, and that's just a spring energy at this point. Spring energy is just given by half k x naught squared. Now the question is, what is x naught? That's what we need to find out. Remember that what was the natural length of the spring? It was over here, right here. It hits at I think 8D over here. It is given right over here. So from 8D to 12D, the compression is 4D. So I'm going to write 4D square over here. So if we equate both these, 12 E naught, obviously I don't need E naught in my answer. So we can find E naught easily, right? Because E naught is just the total or net potential energy over here. So I'm going to draw a triangle, and this is obviously theta, and that's 12D over here. I'm looking for height at this point. I'm going to say that sine theta is opposite over hypotenuse. So the value of h comes out as 12D sine theta. So if we now conserve the energy, the initial energy is mgh. Let me make some space here. mgh, h is 12D sine theta, and that is equal to half kx square. So half k, and square of this is 16D square. I'm going to take out 1D from here. Cross multiply 2, I think. So 2mg, in fact, 2 times 12 is 24. So 24 mg sine theta is equal to 16 kd. I'm going to divide both sides with 16d. In fact, I'm going to cross this out. 8 times 2 is 16, 8 times 3 is 24. So 3 mg sine theta over 2d. That should be the value of the spring constant K. In the next question, we are given that a potential energy of the spring is graphed along with respect to the position, and this is how it looks like. On the same graph, we need to label the mechanical energy total and the gravitational potential energy. We know that at x equal to 12d, obviously it stops, right? So there is no kinetic, there is no gravitational because it is considered zero. So total mechanical will be same as the spring that it got here, and that has to remain constant. We already found that earlier. So 12 E naught will always remain same because there is no energy loss. Now for the potential, we already agreed that it is zero right here. And another point is given in the question itself. 10D, it is 2E naught, right? At 10D, the potential is 2E naught. So I'm going to mark at 10D, the potential is 2E naught. And it has to be a linear because gravitation energy is given by mgh. So there's no square or any funky business here. So that's just going to be a straight line. Keeping those two things in mind, if I draw a straight line, that's going to look something like this. The next one, the last one is determine whether the speed at 9D is greater or less than the speed at 8D. So once again, we need to conserve the mechanical energy, right? At 8D, what's happening? It hits the block, right? It hits the block. It hits the spring, sorry. So spring energy is 0. I'm going to say that at 8D, the spring energy is 0. Uh, Potential energy, again, this is at 8D. So 8D, 12D, the difference is 4. So that has to be 4E naught. And in fact, why am I even doing all this? Because I can just write the total mechanical energy is 12E naught, right? I don't really have to worry about the other things. Then I can just say that at 9D, there's definitely a spring energy now. So spring energy will have some value. Gravitational energy between 12 and 3, there is a 3 E naught difference, and there will be a kinetic as well. And we need to compare the speed, right? So ultimately, we need to compare the kinetic energy. Here, the kinetic energy is the difference, which is 8 E naught. All right, now I know that this has to also sum up to 12 E naught. Now, can we figure out the spring energy somehow? I think yes, because the spring energy is again given by K over 2 X naught square, where X naught is the compression. So at 8D, it was at natural length, and now it is compressed by just D. So it is K over 2D square. And what is K? From part B, we can figure out the value of K, because if we just equate this mechanical energy with this, I think we should be able to get the value of K. Let me just do it over here. So 12 E naught is equal to half K 16D square. This will be 2 times 8 is 16. So I have 12 E naught over 8K, sorry, 8D square. That should be the value of K from here. So 12 E naught over 8D square. I'm going to sub in over here. So if I sub in the value of K that we just found, which is 1/2 as it is, the value of K is 12 E naught over 8, over 8 D square times D square. So these two are gone. 2 times 6 is 12. So I have 6 E naught over 8. 6 over 8 is 0.75 E naught. All right, this is what I'm going to sub in here. So this is 0.75 E naught. 3 plus 0.75 is 3.75. So 12 minus 3.75 is definitely 8.25 E naught. So 8.25 E naught is clearly more than the kinetic energy at D. So the speed is definitely going to increase at 9D. They're also asking how we can justify using the graph that we have in figure 6. So this is what we can write. We can say something like at 8D to 9D, we can see that the decrease in the potential is from 4E to 3E. So there is a decrease of minus E naught. At the same time, the spring potential is getting increased by less than E naught, because if you see at this point, this is not E naught, this is little less than E naught, right? So since this is less than E naught increase, this is a decrease of negative E naught, the total change is negative. But if I want to conserve the mechanical energy, I have to add something more to it so that it again adds up to 12 E naught. So I have to add a positive number, right? In order to keep the same mechanical energy, the kinetic energy has to increase so that it keeps the same mechanical energy. That's how we can justify it. Alright guys, I hope you liked this video. If you did, please like and subscribe. And if you need private tutoring, feel free to reach out. Thank you.